Today, we're going to talk about one of the most incredible stories in the history of digital security. It's a story about an idea that promised perfect, unbreakable encryption, but instead, it became one of cryptography's most spectacular failures. And then it came back, decades later, in a way nobody could have predicted.
So that's the big question, right? How did something that seemed so flawless go so wrong, so fast? It's a story of pure genius, a single fatal flaw, and an amazing comeback that is literally shaping the future of security as we speak. So let's get into it.
Okay, so this whole thing starts with a puzzle. A really simple one, actually. Something you could imagine trying to solve with, well, a backpack and a bunch of different weights. But don't let the simplicity fool you. This little puzzle is actually a mathematical monster in disguise. The official name for this is the subset sum problem, but most people just call it the knapsack problem. And it goes like this. Imagine I give you a pile of rocks, each with a very specific, weird weight. And then I tell you, okay, find the exact combination of rocks that weighs precisely, say, 100 kilograms. Sounds pretty straightforward, doesn't it? But the difficulty just explodes as you add more rocks to the pile. And here's where it gets absolutely wild. If you have like 5 items, you could probably figure it out with a little trial and error. But what if you have 500 items? Suddenly, the number of possible combinations becomes, well, it's just astronomical. We're talking about a number so big that a supercomputer would need literally centuries just to check them all. It's practically impossible.
In computer science, this kind of problem has a very special name. It's called NP-complete, and you can just think of that as a certified top-tier hard problem. It's like a mathematical Mount Everest. It's easy to describe, but it is brutally, brutally difficult to solve. And for cryptographers back in the 1970s, that difficulty, well, it looked like a golden opportunity. The idea that sparked this whole thing was absolutely brilliant. They thought, what if we could use this incredibly hard problem as the basis for a lock? You could build a public lock that anyone could use to encrypt a message, because scrambling the information is easy, but unlocking it, that would require solving the knapsack problem, which, as we just said, is pretty much impossible for any outsider. And that's exactly what the Merkle-Hellman system did. Your public key was just a really, really hard-looking knapsack problem. But here's the secret sauce. The private key was a trapdoor. It was this hidden piece of information, a special secret list of numbers called a super increasing sequence. Now, the trick with these numbers is that each one is bigger than all the previous ones added together. This creates a kind of amazing shortcut that makes the puzzle incredibly easy to solve backwards, but only if you have that secret list. So for everyone else, it's an impossible puzzle. For you, it's simple math. It seemed absolutely perfect. But, as you probably guessed from the title of this whole thing, that glory was not going to last. The system was about to face a truly spectacular fall from grace. And the collapse was just breathtakingly fast. I mean, look at this. In just 6 years, the knapsack code went from being hailed as a major breakthrough to being completely and utterly obsolete. It was proposed in '78, celebrated as the next big thing, but by 1982, a cryptanalyst named Adi Shamir, yep, one of the inventors of the RSA algorithm, found a crack. By '84, the whole thing was shattered. So what happened? What was the fatal flaw? Well, ironically, it was the trapdoor itself. That special mathematical structure, that super increasing sequence that made the puzzle so easy for the owner, it also left behind these faint, telltale patterns in the public key. It created a subtle, hidden weakness that Shamir's algorithm was able to sniff out and exploit. The very thing that made it work was also its undoing. And this taught the entire cryptography community a really important, kind of painful lesson. Just because your code is based on a famously hard problem, that does not automatically make it secure. You see, if the process of building your lock leaves behind a blueprint for how to pick it, the strength of the core problem doesn't matter one bit. And this wasn't just a one-off failure. The fall of Merkle-Hellman started a domino effect. One after another, new and improved versions of the knapsack code were proposed, and, you guessed it, almost all of them were eventually broken too. An entire branch of cryptography just withered away. But just when everyone had written off the knapsack code as a cool but failed idea, a historical footnote, the story takes a wild, unexpected turn. Decades later, that core idea was about to make a comeback. Yeah, it turns out the original concept wasn't necessarily wrong, it was just the implementation that was flawed.
And now, in the world of post-quantum cryptography, the race to build codes that can resist attacks from future quantum computers, the ghost of the knapsack problem has reappeared. This comeback is happening in a field called lattice-based cryptography. Now, you can kind of think of it as a multidimensional version of the knapsack problem. Instead of a single line of numbers, you're dealing with a complex crystal-like grid, or a lattice. And finding your way through this grid is an even harder problem, which gives us a much more robust foundation to build a code on. And when you put the old system side by side with the new one, the difference is just night and day. The old system used a specially structured problem that, as we saw, had that hidden flaw. These new systems, they're based on the hardest possible versions of these lattice problems. The original security was just assumed to be good. Today's versions are provably secure. It went from broken to a leading candidate for protecting us in the quantum era. What a turnaround. And here is the key innovation. This is the part that cryptographers literally dream of. These modern systems have something called a worst case to average case reduction. Now, in simple terms, that just means that to break a normal, everyday version of the code, you'd have to be able to solve the absolute hardest possible version of the underlying math problem. This is a huge deal because it guarantees there are no hidden weaknesses or easy shortcuts, like the one that doomed the original. So, after this incredible journey of failure and then redemption, what is the knapsack's final legacy? Well, it's way more than just a cautionary tale. The DNA of that failed idea is now a core part of the very foundation of modern security. Seriously, the concepts it pioneered are absolutely essential for creating the advanced, quantum-resistant tools we're building today. We're talking next-generation digital signatures and even this wild idea of encryption that you can do math on. It's gone from a broken lock to basically a master key for the future. In the end, the story of the knapsack code is this powerful reminder that in science and in technology, failure is so often just a stepping stone. The lessons we learned from that spectacular collapse over 40 years ago are now directly influencing the tools we're building to protect our digital world for the next 100 years. And that leaves us with a really fascinating thought to end on. This was the story of one idea that was maybe ahead of its time, or maybe it was just missing one key insight. And it just makes you wonder, what other supposedly failed ideas are out there right now, just waiting for the right moment, the right technology, or the right person to come along and change everything?